So hello everyone, I'm going to talk about the Dora project and how we implemented distributed data flows with the help of Zenoh. So it's kind of an experience report, I guess, for the people that heard the talk before. So I'll first start with an introduction to the Dora project, and then we look into the problem of sending messages across machines that are not directly connected to each other, like separated by firewalls because one is running in the cloud and one is running in your home Wi-Fi or something. And we discuss the challenges and show how Zenoh helped us to resolve those. So Dora is a data flow framework, so similar to ROS or ROS2. And we aim at like robotics and AI applications. And the idea of a data flow framework is that you model your application as a directed graph of operations. So in this example on the right, we have a webcam node that acquires images from a webcam and sends them as output. And then we have like another node, object detection, that looks for common objects such as people or chairs or anything like that. And if it detects one using an AI model, for example, then it sends bounding boxes output, and the plot node then combine these two outputs and like draws a circle or a rectangle around the detected objects. So this architecture has the advantage that you have a clear separation of these components. So you have very good isolation. So if one node goes down, you can just restart it. The other nodes can keep on running. And you also have the option to split this across multiple machines. So if your webcam is running on like a small robot or something that doesn't have a lot of computing power, then you can have a powerful machine that does the object detection for you and sends the output back. And because you have these clear boundaries, you can also observe things for debugging. So you can just tap into a live system and see what's happening there. So the motivation for creating another framework, right, I mean there are a few already, is that we wanted to focus on simplicity and like getting started quickly. So we don't want to focus on just C and C++. We have like support for all these various languages. We support Rust as one of the main languages and Python. And you can choose that between, like for each node individually. So you can have a Python node because that's easier for interacting with some AI models, for example. And that one can easily communicate with a Rust node that you write for high performance, for example. We also support C and C++, which is good for legacy applications and also if you have like C libraries that you need to use. The configuration is done through a short YAML file, so you just you list all the nodes, you define their outputs, and you say, in this example on the right, that your inputs are mapped to some output of another node. We don't have an own build system. That was like an explicit non-goal because there are so many build systems already, so you shouldn't have to learn a new one, so you just plug in your build command, basically. So if you have a Rust node, you use cargo. If you have a Python node, you use pip. And we just run these commands and don't like have our own version of make or anything like that. And because we have these clear boundaries between nodes, we can easily reuse nodes that someone else wrote. So we have this node hub, and there are like various nodes for AI models or for like accessing your webcam, and you could just plug them in and just write the remaining nodes yourself. So if we take a look at the general design of Dora, we have a central coordinator that is orchestrating all the things, so it controls data flow execution, and you have a command line that you can use to spawn data flows, to access logs, and to stop data flows again. And the actual execution is managed by these daemon instances, so each of these machines has its own daemon. And this daemon is responsible of building the nodes and spawning them. And we chose to do that as a separate process for each node, to really have these isolation guarantees between them, but also to give users full control of the execution. So you have access to the main loop. You just include the library to communicate with the daemon, but you can otherwise do whatever you like. You can access system libraries, you can pull some network interface, whatever you want. the purpose of the daemon is then to forward the messages. So if you want to send some message as output, you just send it to the daemon. And the daemon will take care of where it should go. And for that we use shared memory if the receiver is on the same machine and the network otherwise. The daemon is also responsible for killing unresponsive nodes or restarting them, or like handling stop commands sent by the CLI. So why did we choose this design? Because we want to support so many languages for the nodes, we wanted to keep the API as simple as possible. So the nodes shouldn't need to care about network connection or the topology or include any other complex code, but instead they should just focus on their main application logic, and everything else should be handled by the daemon. So the daemon is the one that is basically the data plane. It's communicating with these other daemons and figuring out how to send these messages. We have a central coordinator, which is of course a single point of failure in a way, but this makes the whole design much simpler, so we still chose to do that. For example, it allows us to do a synchronized start. So if some nodes are still building, we wait until everyone is done so that the whole data flow can start at the same time. As I said, for local receivers, we use shared memory because messages might be big. Because if you have image data uncompressed or video streams, then that's a lot of data and you don't want to copy it unnecessarily. So the idea is to have a memory region that holds your message, and you just construct your message directly there. So you don't create your message on the heap and then copy it over, because then you have a copy again, but instead you construct it really into that shared memory region, and then you tell the daemon just the ID of this region, and the daemon can forward it to the other local receivers. Those can map it and then access the data directly without any copy in between. But one challenge that arose in that is that different languages have different data formats for representing types. So string types in C are like an ASCII encoded, array null terminated at the end. Rust strings are UTF-8 encoded and don't have like a null byte at the end. So you need some common data format for this all to work. For that we use the Apache Arrow format, which is like a cross-language data format that is intended for shared memory. It supports all the programming languages that we need, and it has first-class support for immutable data, because we cannot, if you want to send a message and that message is sent to many receivers, you cannot mutate the data because it might be still needed by some other receivers, right? And we also have lazy operations in Arrow, which is important because you don't want to copy the data. So if you have multiple operations, these are not applied until you write out the data in the end, ideally directly into the next shared memory region so that you can send it as an output. And this way you can do zero-copy message passing, but also zero-copy message processing, where you never copy a message in its original form. We always do something with the message. So the question that then came up was, how do we do messages to remote receivers? So we cannot use shared memory because we don't have shared memory if it's like two different computers. So we need to use a network connection. So in this example on the right, we have node on machine A, a Python node that wants to send data to a node on machine B. So the first idea was, okay, let's just open some TCP connection or something like that. But that leads to a lot of connections, that leads to additional complexity in the nodes. So now the nodes need to know again where the receivers are and how to open connections to them. And also sometimes they're in different networks and you cannot really open a direct connection to them. So this was quickly ruled out. The other idea was to use the existing connections through the coordinator. So just let the daemon forward the message to the coordinator, and the coordinator sends it to the other daemon. And this way we get the message also on the receiver. But this has like a bottleneck because all the messages go through the coordinator and there's only one coordinator. So if this one is overloaded, then the whole thing becomes slow. And there's also an additional network hop, but that shouldn't be that big of an issue if you're not like deploying the coordinator to some on a different continent or something. So the main issue was that. So we decided, okay, let's try to connect these daemons together at this level. So the nodes can stay simple, the daemons handle the complexity, and relieve this control plane with the coordinator out of the equation and let it focus on control plane stuff. So simple approach to connect the daemons could be that each daemon opens a TCP port on some local port number and knows its own IP address, right? So it sends the IP address and the port number to the coordinator. The coordinator can then inform the other daemons about these IP addresses and port numbers, and then we can open like a TCP connection from daemon A to daemon B. And once this connection has been established, we can reuse that to forward messages that should like cross this daemon boundary. Unfortunately, this only works if the machines are like inside the same network, because if you go through the internet, then there are typically things like firewalls that block incoming traffic. So you could, of course, work around those if you create a manual exception in your firewall or firewalls, because there might be multiple ones. But this is not like the ease of use that we want to achieve. And also there are nets, network address translators, that assign a new IP address to like a whole subnetwork. So because public IP addresses are limited and expensive, you typically don't have like an IP address for every device in your home Wi-Fi, for example. So if we do a quick example, in this case, daemon B is behind the net. So if it communicates with the coordinator, it appears as that connection is coming from a different IP address as the daemon think that it has, right? So this 192 IP address is an internal IP address that is not valid on the internet. But the daemon doesn't know that, so it still sends a message with its internal IP address and the port number to the coordinator forwards it, and then we fail to open a TCP connection because it's an internal address, right? So, can we bypass these nets and daemons? There are techniques to do that, yes, but I would classify most of them as hacks because they kind of want to fool the nets that this is an existing connection, even though it's an incoming connection, so you kind of, change your IP packets and try to modify them in a way to fool the nets. And none of these ways is really reliable. So, unfortunately, that meant for us that daemon-to-daemon connections directly using such TCP connections are not practical. So we ended up deciding on using some proxy node, right? So we have a proxy at like a location that is reachable by both daemons. We open outgoing connections from both daemons to this proxy. Outgoing connections are fine because firewalls let them through, and nets are like designed to work in a way that doesn't affect outgoing connections. So if we just create these connections, then once these connections have been established, we can just let the proxy forward the messages back down, because these connections are like bidirectional. So what would be criteria for proxy server for our project? So of course it needs to be reliable, we don't want to lose messages, it needs to be scalable, because we don't want to have like a single proxy and it's like the approach with the coordinator again. So we want to be able to spawn multiple proxy servers to scale things up. And of course we need to be fast, we need high throughput, because like we send image data, and we need low latency, because if a robot is crashing into a wall and you type stop, you don't want to like have a delay in that. And we need complex network topologies, because we want to be able to run certain nodes in the cloud and others in your home Wi-Fi or on the robot or something. So we ended up looking at Zenoh, and we saw that graph and thought, okay, that's a good candidate. What we really liked is that you can have both these peer-to-peer connections, as Angelo mentioned, and routed connections. So if the daemons are in the same local network, then they don't need an additional network hop. They can just directly connect to each other. But if they are in different networks or behind a firewall, Then you spawn a Zenoh router at some intermediate location and let it forward the messages for you. I think I don't need to repeat the details of Zenoh, but it's a PubSub protocol, so it works a bit different than a TCP connection that is point-to-point. So you publish on a topic, and everyone that is interested subscribes to that topic. So, which is also convenient for our use case because all the daemons that want to receive a message from a certain node can just subscribe to the topic, and we don't need to send duplicated messages to different receivers. And so we ended up with a design like this. So for the connection to the coordinator, we decided to keep the TCP connection for now, mainly because we want to try gRPC for that in the future. Because that should be easy to work with the CLI. So the CLI wants to connect to some coordinator running in the cloud, and gRPC seems like a good candidate for that. But for the daemon connections, we choose to use Zenoh. And as I said, if they're in the same network, we do a peer-to-peer connection. And otherwise, if there's like a net involved, we spawn a Zenoh router, or let users spawn a Zenoh router, and use that for forwarding the messages. The topic format is not important in detail, but basically we decided to have like an expressive format. So you have like the ID of the data flow run in there, that you can spawn multiple data flows that are identical at the same time without affecting each other. But mainly you have like the node ID that is the sender and the ID of the output inside that topic. So if you have like some debugging concerns, then you can just subscribe to that topic and see what's sent on this. And the wildcard support makes it really nice so that you can listen to all data flows or listen to all outputs, whatever you like. So the design at the end, or like the implementation, works this way: that you start the Dora coordinator at some machine with a public IP. It doesn't really need to be public, it just needs to be reachable by all the daemons. And then you start the daemons on all the machines. You assign each one a unique ID so that you can reference them later. And you need to tell them about the coordinator IP address, or like URL or something. So this one is still in plan to change. And as you see, the syntax for doing that is also still unstable, so this is a quite new feature. But we plan to decide on the syntax soon. In this example, we have two nodes running on machine A, and the third one is running on machine B. And our goal was that you can just run the Dora start data flow command, and then Dora will figure out, okay, should I use shared memory for that, or should I use Zenoh for that? And it will also, on deployment later. First, a bit on the configuration that is required. So Zenoh has auto-discovery support for local networks. So it sends multicast packets inside the network, and everyone that receives this can directly connect to each other. It also has a GOSIP protocol. So new nodes that join are like told all the IP addresses and or like different connections of the other peers that have been discovered. But if you have like a firewall or a net in place, then you need to specify the endpoint addresses manually. So for that, Zenoh uses a JSON file. I think that's...
It's a JSON or JSON file. We support multiple formats, but
okay, but you have like a configuration file.
Yes. And that's a JSON file what you're showing. What you're showing is JSON 5.
Okay. Yeah.
Because otherwise you get codes between the lines.
Yeah. But it was copied from your website.
Yeah. So that's JSON. That's JSON 5. So no.
Yeah.
That's perfectly fine. It's legal and it's JSON 5.
Yeah, that's true. Yeah, exactly. So in this case, you need manual configuration, and you do that using an environment variable where you store the path to the file, and Dora will detect that and bypass this to the Zenoh initialization. So the part where Angelo had this default configuration, there like this configuration file goes. So because it's part of the initialization, it means that you currently have to restart Dora if you want to modify this Zenoh graph. I think there's an unstable feature to update the configuration in place, but I don't think there's a stable option.
So
yet
there are the endpoint. No, that's available. You can update the endpoints, but so you have to do that. You will do that from from your daemon. I suggest you look at example ZCAM
Okay.
on Zenoh, demos, computer vision.
Yeah, let me write that down.
Oh, sure. But
Yeah.
you will see how you can do that. At runtime, you can essentially change the endpoints.
Okay. Yeah, I just found the functionality to have like the config file or like the whole config updated, but we only need to update the endpoint.
Correct. You can only do,
Yeah, good to know. So with that, like the only remaining question was deployment. So of course the manual deployment always works. You build it on your node, on your local development machine. You copy over the executable and you just specify the path to the executable in your YAML file. But of course that's not really nice and like a lot of manual work. So we're working on a feature to use Git repository. So the idea is that you specify the repository URL and the branch name or tag or whatever. For each node and probably a build command, and then Zenoh will automatically clone the repository on your target machine, build the stuff that you want to build, and then run it. And we also have planned to add support for Docker, so if your node has like system variables or the system environment that it needs, then this might be easier even to just set up a Docker container and download it. Yeah, and other future plans are authentication and like using credentials, because if you spawn something at a public IP address, you should have some way to protect that. Yeah.
Why don't you use Zenoh security? Because you could do that with Zenoh security.
Yeah, that's one of the things we want to do. We just haven't had like time for that. Like as I said, new feature. We just have like a prototype implementation right now.
Okay, because you could use TLS either mutual or in that case.
Yeah.
You do, I mean, you
No, right. But also for the
be lazy, right?
also for the coordinator, where we like,
Yeah.
I think with the switch to gRPC,
That
should
would be a follow-up question for me.
Yeah. For deployment, I mentioned Docker support. We also thought about an option to auto-select from a certain set of machines. So if you have like a pool of machines and you don't really care where it's running, you just want to select the one with the least load, for example, then that should also be possible. And of course, since this is a new feature, we like need a lot of work on polishing, improving documentation. Like the coordinator is not auto-detected right now, but the daemons are. That is not really a nice situation. And also that you also always have to specify this IP address of the coordinator. Like for the CLI, for example, is also not nice, so we try to improve that. Yeah, and then we want to have like some examples at least for deploying to AWS or Azure or something like that, because that was like one pain point where we had a bit of issues with Zenoh.
By the way, I'm kind of pre-announcing this, but we are about to release a free tier for our platform.
What?
A free tier. You know, we have a platform
Yeah,
as a service
for the
free
commercial one. Yeah.
That will be free tier.
Okay.
So you could have your, if you want to have an off-the-shelf, you could have a controller running there.
Mm-hmm. Sounds great. Yeah, I mean, we're also like an open source first project, so we also need an option to have like.
Correct, but I mean that doesn't mean that it's not open source. You can deploy open source software there, but you will have a router running for free.
Okay.
On a public
That's
cloud.
quite nice. Yeah.
Correct, because then you can use. You could have a a Dora. But yeah. Anyway, so I'm giving you the example. This is coming up, but yeah.
Okay.
And we are doing that precisely for facilitating also the robotics community, because each time you want to do anything that is teleoperation, you need to, I need a credit card and I need Amazon, right?
Or some like free credits, but they.
So now you won't need it anymore. Will be announced formally the 23rd. Okay. Yeah. So I didn't say anything. Okay.
Yeah, so that also was my talk, right? So if you want to join us, find us on dorars.ai. We have our GitHub repository link there. We're fully open source, so we always appreciate pull requests and like people joining our discussions. Right now we still have an open discussion about this Git feature, how this should like work with reusing existing clones, because we don't want to clone on every start. So yeah, thank you for listening and please join us.